Thank you, and good afternoon. I heard you saying yay to many questions, so I'll ask you one. How about differential equations? Yay. Okay, great. So now I know what to talk about. So there will be a little bit of science in here, I'm afraid. But of course, I mean, the cool thing is that these brain-inspired computing is actually pretty close to real application. So you know this object, you all carry it with you, and it has some interesting features. Now, it's what physicists call, and I'm a physicist, call a complex system. It has these 10 to the 15 connections and 10 to the 11 nodes that we call neurons that do interesting things. And it's not isolated. It never works like it is here on this slide, but it always interacts with the environment, and in particular also with other brains. You talk to each other, and that's very important because it leads to an effect which we call self-learning. So it doesn't need any software, but it really organizes itself according to organizational principles and learning mechanisms in particular. And of course, what's interesting for computer science is that it seems to be somehow energy efficient, so the power, not the energy, but the power is about 20 watts or so. And it is fault tolerant. You're all losing a cell per second at this very moment, so 100,000 a day. And it still kind of works. It gets worse when getting older, I know that, but it's still rather fault tolerant. And imagine to do that with a microprocessor, killing a transistor a second. It will soon start working. It will not be what we call graceful degradation. It will just be sudden death. And this doesn't happen to us. So it's clear if those computational principles could be transferred to an artificial system, it would be quite cool, and it could be what people call a game changer in computing. And we call that neuromorphic computing. And what is it? I mean, many people say it's building brains. I think that's not really true. What we want to do, this is my definition here, it's implement some aspects, and there is, of course, only some aspects of structure and function of biological circuits to images in electronics. And those could be analog or digital, I don't care. And actually, I will talk about both today. Now, what is structure? It's the structure that we know from the nervous system. There are cell cores, there are networks which are formed by axons, dendrites, and of course, the connections between them, which are the synapses, which are actually chemical, very complex chemical objects. Now, there is function, of course, and that's at the end more important. There is local processing in a cell, kind of integration. There's communication between the cells, and of course, the most important thing, I said that already, is learning. And why are we going to do, why I want to do it is, I mean, there are some interesting things here that evidently are interesting. Energy efficiency, I said that already. Compactness, the brain is a rather compact system compared to the supercomputer. Fault tolerance, speed, I will talk about that. Configuration and learning replaces software, that's really important. And scalability. Now, of course, if you look to conventional computers, you hear say energy density versus clock speed. In this diagram, you see that conventional computing is going exactly the other way compared to the brain. The brain is in the left lower corner, and this is a log scale, as you can see. And all these modern processors move out. They go to a higher integration density, to some extent also to higher clock speed, although that has stopped. So it is clearly a totally different concept that's behind the brain, and we have to discover how it works and then transfer it to modern computer architectures. So why has that not been done? Because we have electronics, we had electronics for a long time, we had microprocessors for a long time. Why are there no neuromorphic chips in your cell phone? And of course, there are some challenges here, and the challenges are you have to realize the connectivity, that is one thing. You have to think about where is actually the information stored, and that goes to the concept of distributed memory, where we don't really know how to do this. And the other one is, of course, the most important thing. How can we make these systems configure themselves and being able to learn? So, of course, embarking into work like that, you have to ask yourself first, why are you doing it? What's the goal? And there are exactly two goals. One is to understand the brain, the biological system, which is a basic science goal and is a very cool goal. It is comparable to understanding the universe, I would say. It's of same importance. And the other one is, and that you cannot do with the universe easily, is to transfer it to applications, to computing that is not applied to data from our eyes and ears and other parts of the body, but to generic data, for business data, for example, science data or whatever. And if you want to do that, you have to build a model to test your ideas, because there are many people write me mails and say, I think I have an idea how the brain works. And then there's an endless letter explaining all kinds of ideas, and I always say, well, I'm a physicist, and you have to test your ideas. You have to build an experiment and then verify your theory or do the opposite, kill your theory, which is equally important, of course. And so we have to build this model system. And building a model system, there are, again, basically two ways to do it. One is to build a numerical model, where the quantities that represent the cells in your brain, like currents, capacitances, charges, and things like that, are represented by numerical values that are then used by programs that are executed in some kind of a computer architecture like a von Neumann and Turing machine to calculate how the brain works. And it's a numerical calculation. And there is another approach, and we are doing this in our own group. It's part of the Human Brain Project, which are called physical computing, where there is a non-Turing approach, so there is no program and there are no numbers. So there are differential equations, but they are not used by doing numerical integration and computation, but by building a physical model. So charges are represented by charge, and voltages by voltage, and so on. So how can you do that? We know there are charges moving in our brain, in the cells, through the cell membranes, and there are currents and voltages, and the same happens in transistors. So the basic idea is you just take a transistor as it is, and you try to configure it, maybe with some other transistors, so that it works like a brain cell. Now, transferring biological principles to computing, of course, is an old idea, actually going back to people like von Neumann and Turing themselves. They suggested that we could have architectures that look a little bit like the brain. Now, biologists would say this is not the brain. And I would fully agree. On the other hand, there are aspects of the brain that are the basis for what we call ANNs, or artificial neural networks. So what you see, there are layers of cells, and those layers of cells are interconnected by these lines, which represent inputs to the neuron that are weighted with some factors, and then send the information that gets out of the neuron into the network. And the idea is that you have an input pattern that you know, like the cat there, and one of the output neurons fires and say, this is a cat, or this is a dog, or whatever. And you know how this works. The concept here is that a neural cell is an integrator, and it's a spatial integrator. It integrates information in space from many different other neurons, and basically what it does is it's just a sum. It calculates a sum. Of course, that sum is weighted by factors. So you have to do a multiplication, many multiplications, and a summation. And then, as a result of that, the neuron perform some kind of nonlinear operation, like just a threshold or logistics function or whatever, which we call the activation function of the neuron. And this kind of concept, of course, you have to train the weights. This kind of concept is, at this very moment, incredibly successful. There is what many people call deep networks or deep learning, which are just networks which are many, many layers. More than 3, I think, qualifies as deep these days. And so what you have to do is to do all these additions, summations, multiplications, and calculation of response functions. And what people do is they now build special computers for that. This is a computer that's located at the Alphabet company. Google is part of that, but this is DeepMind in particular. They build this machine, and this machine actually trains a network to play Go. You know, you have seen that it was very successful and very spectacularly successful. And what you see here is the training method, which I cannot describe in detail, but you can ask me questions. What I would like to point your attention to is that this network actually uses more than 100,000 games that have been played before for learning, and then there are hundreds of millions of games the machine plays against itself. And at the end, you combine the two things, and you get a system that very successfully plays Go. And of course, there's a price to pay. I mean, the experiment to train these things is many, many months, almost a year, and it's sort of almost a half a megawatt machine. And so that's very expensive in terms of energy. It's very expensive in terms of time. It's very expensive in terms of data, of known data, games that have been played before. And very importantly, this machine will never beat you in tic-tac-toe. Okay? So it can just do one thing. It can play Go, and it will never play tic-tac-toe based on the experience that it gained from playing Go. And of course, that's a fundamental difference to our own brains. Our own brains, we always update our knowledge. If we have seen a cat The step to a dinosaur is not so big, okay? If you have seen many cats and you see a dinosaur, you say, oh, that looks a bit like a cat. It has some special aspect. It's bigger and maybe a longer neck and something like that. But it's the same concept. You don't have to look to another 10 million dinosaurs to know what a dinosaur is. So there is this concept of continuous learning, which is not present in these systems. And I would claim that one of the reasons these systems are still not like the brain is they lack one aspect totally of our brain, that's time and temporal integration. I said the neural networks, they actually do spatial integration, but our own brain cells, these are two neurons here interconnected by this gap that we call a synapse, is performing temporal integration, which is indicated in this little cartoon. At the bottom, you see for the so-called presynaptic neuron, the one which provides the input, one of these input spikes, and the receiving neuron just does these little wimpy, weak response, okay? If you have a burst of spikes on the input, you see that there is building up a voltage in the cell, and then suddenly this nonlinearity sets in, and you get an output spike. And in the classical neural network, this can only be done if you integrate spatially. Here you also have temporal integration. And that's a thing which is not present in all the analog neural networks, like the artificial neural networks that we use today. So what is time and spiking good for? I have 4 points here. First of all, it's sparse information coding. We can actually code information by just one spike or a correlation of 2 spikes by knowing the time of this spike, of this action potential. There are so-called plasticity mechanisms, timing-based plasticity mechanisms which lead to learning, local learning in the network. And there is something like what we call stochastic computing. There is stochasticity. If you solve a problem with your brain, like you grab a bottle of beer or something like that on the table, there are many different ways to do this. You can have a different path for your hand, you can hold your fingers in a different way, but they all somehow lead to the goal. But there is something like a free will. You have a free will. You can grab the bottle like that or like that, which may not be very impressive free will, but if you think about it, it's really your decision. And I would claim there is stochasticity in the system that really supports this kind of free will, and that is also a temporal effect. It really requires time coding. Now, these things are certainly very useful, and I would also claim that they will lead to energy efficiency and computational advantages. Now, the question is how do you implement that? Basically, digital, the world is digital. There are digital summits, and there's a digitization agenda of the European Commission. So it's clear that the decision has been taken that the world is digital, and it has big advantages. Digital values are then represented by physical variables, and if you build digital networks like the one you see there, the good thing is that they are scalable. Yeah? So you have a logic gate. The output is always the same quality as the input. It's always recuperated. And you can build networks of billions of these logic gates, and they are still completely scalable, provided that you can pay for the silicon area. Of course, the problem is that if you calculate something like an exponential function, it's very expensive because you have to do a Taylor expansion or use very expensive lookup tables. Yeah? Then there is analog computing, which has been advocated a lot in the past. When I was young, I still worked with analog computers, believe it or not, tracking particles through magnetic fields. Now, they are great because they have, in principle, continuous variables of physical quantities. The problem is they are not scalable at all. If you have many of those gates, the signal just degrades, and you can maybe build tens or 100 of these things, but certainly not a billion. Now, nature has found something interesting. It's what we call a mixed signal approach. So there is local analog integration in the neurons, as I have just described, which is very energy efficient, very, very compact. But then the transport of information to the next cell is binary, but continuous in time. It's not clocked, but it's binary. All spikes are the same to some extent. And of course, that system is completely scalable because the output of a neuron is just a stereotypic pulse. So it's making, in a way, the best out of 2 worlds. Now, one way now to study this is to just dump it on a big computer. This is work that is also done in the part of the Human Brain Project, is simulation of brain structures on supercomputers. This is an older work by Markus Diesmann from Jülich Research Center in Germany. And he worked in Japan there on one of the big computers, the K computer, and he simulates networks of 10 to the 9, a billion neurons. That's really huge. Very, very simple neurons, I have to say. And he puts it on 60,000 processors, which are in the supercomputer. And what you see is you can make bigger networks by using more processors. Basically, for computer scientists, it's a study of weak scaling, and if weak scaling works, then the compute time should be constant, independent of the network size. And this is what you see here, the lower dots, they are constant. Well, if you look, they are not really constant. They are taking off. In effect, it's a log scale, so weak scaling holds to some extent, but not really perfect. And of course, the reason is that there are more neurons than processors. But that's a detail here. What I would like to point your attention to is the absolute scale on the right side. To simulate 1 second of biology, you need 1,000 seconds. To simulate a day, you need 1,000 days. And a year, you need 1,000 years. And many processes of learning and development in the brain actually take days or weeks or years. So it's clear that they are not accessible by this kind of concept. And this is why people have invented neuromorphic computing. And there are now in the world like 3 large-scale neuromorphic computing concepts and facilities which are called SNiC-NL. Then there is IBM True North in the US, SNiC-NL is in the UK and Manchester. The inventor of the ARM architecture, Steve Ferber, works on that. IBM in Almaden Research Lab, and our own approach, which we do in Heidelberg, and together with other European groups also. Now, it's interesting to see that they are really doing things differently. And I think the complementarity is important because we haven't found the ideal or good solution. So in very short words, the SNiC-NL is a system of many, many telephone processors, like 500,000 at this moment or 1 million in a couple of months from now. And they just have a very, very efficient brain-like communication protocol to communicate by spikes. IBM is going away from microprocessors, no more for Neumann machines, and they build special circuits, but they are fully digital. Fully digital special circuits with relatively simple neural models. Our system is mixed signal. It's a little bit like the brain, I hope. And it has this approach of having local analog computation, so it's partly an analog computer, but all the communication is a binary. Now, these are the machines. I now focus on the Human Brain Project activity. You see the logo there at the left. HBP means Human Brain Project. These are the 2 machines that are available now. And I just would like to point your attention to the fact that there are real computers now that look like the server you may have in your own university. It looks like a plain normal computer, but they are special computers, because they implement these new architectures. So on the top, you see Steve Ferber's machine in Manchester, a many-core numerical model system, as I said, 500,000 ARM cores, and it's running in real time. That's interesting. It means a day takes a day. And that is huge progress. It's also interesting if you want to hook it up to robots, because robots have to do real-time movements because of inertia, and so you cannot be much slower or much faster. So it's very nicely usable for robotics applications, for example. At the bottom, you see our system, which looks kind of similar, but it is fundamentally different. It's what we call a physical model system. It has, in this machine, 4 million neurons and 1 billion synapses. And an interesting aspect is that it runs in an accelerated mode. I will explain you on the next slide. So it runs 10,000 times faster than biology. So a day is 10 seconds, which is good for learning and development, which is bad if you want to hook it up for robotics, for example. So very shortly, what's the SNiC-NL? So it's a many-core system. I said that it consists of relatively simple ARM cores that even have only integer arithmetic. So it's really fun to program these things. It's a real challenge. You should try. It's actually available on the web. And the real thing is that it has this high-speed packet-based communication. It's like a little internet between the nodes, but the packets are really, really small, and they are optimized for spike communication. So that's the SNiC-NL system. This is our system now, and you see the circuit again, which is a very simple circuit. You all know that from school. You can easily calculate the dynamics, the time development of that circuit. So it's a resistor and a battery and a capacitor. And in a way, it emulates part of the cell membrane. The differential equation, which describes the voltage dependence, the time dependence of the voltage is just written there. And of course, if you want this in a circuit, you need some nonlinearities for the spiking. You need these sums there, which are the synaptic inputs. But the important thing is, how does this system know how fast to run? There is no clock there. So the speed actually comes from the physics of the components. It's just the time constant in this very simple circuit. Of course, at the end, there are more complex circuits, but the physics of the components selects the time constant. And you probably know that capacitances in microelectronics are typically small, like femtofarad or something like that. And conductances are good. Silicon, in particular doped silicon or metal, conducts very well. This is in complete contrast to biology, where capacitances are large and conductances are small. And as a consequence, the time constants naturally of electronics are much faster. This is why computers are fast. So what we now try to misuse this speed to emulate the physical performance of the system, but in an accelerated mode. So that's the idea. So you typically have this kind of circuit there, where at the bottom box you have a neuron with a capacitor and the conductances, which describe the cell conductances. And the important thing is this blue triangle there. Okay, it puts a threshold. It's the nonlinear response of the neuron. So there is a voltage coming in, it's changing all the time, and if it reaches the threshold, it fires and sends a spike into the network, which is then processed by analog synapses that do all kinds of interesting things. Now, we have to build chips out of that. This is one of our chips, a recent one. You see some parameters there. Differential equations start to be more complicated. There are two now because we have a lot of biology put in there. But what I would like to show you here is this is the chip. It's about 0.5 centimeter by 1 centimeter. And it looks like a tennis court, okay, with a net in the middle and an upper and a lower part. And the net in the middle, those are the neurons. There are not many, like a couple of hundred, 500 or so. But the tennis courts, these big areas, the grayish area, those are the synapses. And it tells you one thing. It's mostly synapses and connections. So all the efforts in our chip go into connectivity and making those connectivity dynamic so that they can actually learn. So it's a chip that is totally dominated by synapses. The ratio of synapses to neurons is typically more than 10,000, which is like in our own brain. Now, this is a little bit of entertainment after maybe tough talk so far. You know what this is. This is a transistor, by the way. And this is a drawing of a transistor, an abstract drawing done by a chip designer, okay? And you know transistors have 3 legs, an upper leg, a lower leg, and a middle leg. And this is source and drain. There is a gate on top which controls the current. And what you can do with these transistors, you can build microprocessors by wiring up 1 billion of them or so on a modern Intel microprocessor. Now, we do things differently, and I show you. By the way, this is about 180 nanometers, something like that, in real life. So I show you how this looks like now. You recognize the transistors, and they're all wired up there, okay, to some kind of a weird network. But if you zoom out, and obviously we zoom out now, you start to see regular structures. You start that regular structures emerge. And those are physical models of synapses. Those are synapses, about 10 by 10 micrometer. If we zoom out further, you see a huge area of synapses, tens of thousands of synapses. They are physically there. They are not calculated. Now at the bottom, you start to see the neurons and the other synaptic field. And now you see many, many chips, like 10s, 20, 50, and at the end it will be about 500 chips. And those chips sit on a wafer, and this wafer carries 200,000 neurons and 50 million synapses. And the thing is, this is what we get delivered by the company that actually makes the silicon. So normally what you now do is you cut this into pieces, okay? And then you build some kind of system from that. So what we decided is not to cut it into pieces, but to leave the wafer intact, to put it into an electronics system with many printed circuit boards. They are all homemade, these printed circuit boards, about 2,500 in our system, basically all designed by students and some technical support. So this is the brain-scaled system, and this is now a big system of, on a wafer, as I said, 50 million synapses and 200,000 neurons, and what we have to do is to make sense out of that. It's a bit like an FPGA. You know what an FPGA is? It's a sea of logic gates, of configurable logic blocks, and you, as a user, you have to configure it. And we have to do the same thing. So we have about 40 megabytes of configuration space to make sense of this. There are conductances, there are time constants, there are learning parameters. All those you have to configure. And you see, if you look at the statistics, 90%, more than 90%, or about 90% is really connectivity, about 12% are neuron parameters, and the rest is just a little bit of extra thing. So how do you do this now? How do you configure this system? Well, we do experiments typically with what we call a hardware in the loop, where we have our hardware, which is the wafer system. It's called the test configuration on the chip, and we read out the performance into a normal computer, which is at the upper left corner, the red bubble. Okay, and then we do some calculations, like learning algorithms, for example, and we send the configuration back into the system, into the chip. And we call this, for obvious reasons, hardware in the loop. So this is the system that we have in our lab. You see a normal, plain, boring computer in the middle, and then the neuromorphic machines, which sit in these these units there. There are 20 of them. And so the red arrow shows configure and load, and the blue arrow shows read. And the conventional computer does what we call calibration, learning. It simulates virtual environments if you want to run virtual robotics experiments, and also holds the data if you want to do data analysis. In the time that remains, I will actually now go through 4 application examples. The first one is a plain deep network, normal feed-forward network, and we just do this with spikes. There's not much point to do it, but we thought we might try it as well. This is a deterministic network. Then I will tell you a little bit about stochastic computing. I will tell you about learning, supervised learning, and unsupervised learning. A deep network, you know what it is probably. I just showed it. There's an input layer where you have some labeled data, like in this case, handwritten characters. Then there are hidden units, and there are visible units which tell you the character was a 1, a 3, a 2, or whatever, okay? And so what we do now with this system, we put it in the loop, we train it, and we get success rates, as you see at the bottom, which are way above 95% or something like that. So that's not very impressive. You may say it's boring because it's just a plain normal feed-forward network that we train with some kind of backpropagation algorithm. But I'm showing you this for a reason which I hope you're kind of impressed. And this is not a computer, okay? It doesn't compute. This thing does not handle any numbers. It's really a physical model. It's just moving charges, like in biology, and it recognizes these numbers like a normal computer does. So it's a physical model that actually does a standard machine learning benchmark task. Here you see the spiking activities in the various layers, and for those of you who have seen spiking in biological systems, it looks a bit like what you record from a mouse or something like that. Next thing, very shortly, you can ask me more questions here because I'm really too short on this, is Boltzmann machines. Boltzmann machines are networks of neurons, like the thing we have seen before, but now they are stochastic. That means their firing probability is not a sharp threshold, but a soft threshold with a certain firing probability. And that's interesting for those of you who studied maybe physics and thermodynamics. You probably know that these networks converge to what we call a Boltzmann distribution. It's actually like the gas in this room or many particle systems in physics. And it does it with a certain energy function. And the energy function contains the W's there, which are the weights. And those weights is what you train. So what would you do that? Why would you do that? It's to learn an internal stochastic model of the input space and to generate or discriminate input data. So what does it mean? I will tell you, first of all, how do you make neurons stochastic? That's an interesting question because if you look at our circuits, they have some noise, of course, but they are pretty much deterministic. If you send in a current, you can predict when the neuron fires. The same is true for your neurons and for biological neurons. If you take a biological neuron in the Petri dish and you stimulate it, you can predict the time it fires. And you repeat the experiment, it will be the same. So there is no randomness, no stochasticity. Still, we need stochasticity. Now, the interesting thing is if we record from the brain of a behaving monkey that does some interesting things like playing a computer game or something like that, which people do with monkeys, and then they record from the brain, they find that the neuron is extremely noisy. And that's not because of lack of precision in recording, it's a feature of the network. And what we found is that this is actually necessary for computing, and we can emulate the noisiness of neurons by putting them into what we call a sea of noise. So you have a big network, and there are sub-networks, little sub-networks, they do different things, okay? And they all do their own things very well. And then we interconnect them. So the activity of the neighboring network to one particular network is just uncorrelated noise. So it's the intelligent activity of sub-networks that produces the noise for the entire system. We call that a sea of noise, and it's also what biologists call an in vivo type condition. So what can you do with this? This is an example. So how do you do learning where you actually produce input, like these handwritten characters, then you clamp the visible units to a particular pattern, you fix them, you reach thermal equilibrium according to the Boltzmann distribution, and then you increment the interaction between any two nodes. So that's typically the learning algorithm. And if the system has only seen these 3 characters there, or numbers 4 and 3 and 0, and then in a way you close your eyes, okay? You don't provide any input to the system. Then what it does, it starts to generate starts to remember what it has been seeing. So it's called a free running or dreaming or a generative mode. So it starts to generate these kind of characters internally, but those are not exactly the one it has seen. If you dream, you never dream exactly what you have seen, but it's somehow distorted. And this is the same that happens in this probabilistic system. Now, what you then can do is to use it for inference, for discriminative applications. You can put in some inputs, which is sort of restricted, where you have, for example, the bar in the middle always switched on, and then it knows, well, it can only be a 4 or a 3, but I'm not so sure. So it's jumping between 4 and 3 and then never to the 0. Well, that's a typical application of stochastic computing. How much time do I have? Not much, I guess. It's basically over, right? Very shortly. One more example is what many people expect us to do is reverse engineering biological systems. I mean, what I've shown you before is not really reverse engineering biological systems. It's more using theoretical approaches and putting them into the system. Here, we use an insect brain. And insects can do what people call multivariate data classification. Insects can distinguish flowers by their smell, okay? And they don't have sensors for roses and tulips and whatever, but they have sensors for chemical substances. So they identify a certain chemical substance, and it's the combination that then identifies the flower. And so what we do is we have these receptor neurons there, Rn, then we do what's called a decorrelation step, and then the association step, where we associate the combination of chemical substances to identify a certain flower. And what we have to do is to do learning by determining the strengths of the lines that connect the decorrelation layer and the association layer. And this is kind of the result, what it looks like. Yeah? So the input data, the spike-coded input data, looks like this random thing there at the bottom. This is where the information is. And if you look to the rays, these are firing neurons. It's like tuck, tuck, tuck. Every little black dot is a tuck, like a radioactive source, okay? And if you look to the histogram there, it's just flat, the statistical histogram. There seems to be no information in this data. But actually, the network is able to reconstruct information. If you look to the output layer, it starts with a flat histogram. After training, there are these spikes coming up, which means the network has learned to identify tastes, for example, flowers or whatever, or in general, multivariate data classification. Final example is a cool thing, which has been done by a bachelor student in our group, actually in 3 months. Now that the system runs, it's relatively easy to do this kind of work. This is an echolocation circuit, which birds have, like owls, for example, barn owls. They sit in a dark barn, and there's a mouse somewhere making a noise over there, okay? And if the mouse is over there, the sound arrives at my right ear before it arrives at my left ear. So there is a time of flight difference or a phase difference, and that phase difference is very small. And of course, the neurons and the synapses in the bird's brain are not very precise. They are these lousy, very bad analog circuits, okay? But there are self-organizing principles like the spike time-dependent plasticity that actually auto-calibrate these circuits. And we have done the same thing, and you see it's interesting what happens. These colored plot there, these are the synaptic weights in the circuit, and they all start at the same value, which is 7. And then we go through the learning process. This is biological time. You have to divide it by the compression factor for hardware. You see that these weights, the importance, and this is self-organized, it just spreads out. It produces some kind of variability. And that's the learning process. And after the learning process, this chip has been able to detect phase differences of about 10 nanoseconds, much better than the birds. That's because it's an accelerated system. But the cool thing is that it auto-calibrates very bad quality analog circuits, which is quite an interesting concept. Okay, I'm basically through. Energy scales, is it all worth it? Well, it's interesting, but there's the energy aspect, and energy you have to refer to some basic operation. Here it's the energy for synaptic transmission in our own brain, 10 femtojoule, and a supercomputing simulation like a joule, or maybe a factor 10,000 less for simpler models, but there are 10 or 14 orders of magnitudes in energy. The neuromorphic systems like Spinnaker and brain scales, they sit at 10 to the minus 8 and 10 to the minus 10. So it's definitely an energy advantage. More importantly, there is a timing advantage. If you go from synaptic activity to development in biology is from 10 to the minus 4 seconds to years. On supercomputers, it's from seconds to thousands of years, which is not accessible on the accelerated system. It's from 10 to the minus 8 seconds, which are easily accessible for electronics to thousands of seconds. So it's really quite a cool thing. There is a follow-up chip now, which is under development in the Human Brain Project, which has lots of cool things. Now we do the loops on the chip. We don't go out to this computer, which is very expensive and very slow. So there are local processors now which can implement learning algorithms, and we have very, very biologically correct neurons now, which will do the learning actually by neuron mechanisms in so-called active dendrites. That's a lot of detail here, but of course, if you want to know more, there is a website. It's very easy to remember, neuromorphic.eu, and you can read a lot about our work. It's a so-called guidebook where you can see what we have done, actually both the brain scales and the Spinnaker system. And if you want to try it for yourself, that's also possible. There is remote access to the systems, and that could be kind of fun. Thank you very much.